Okay, let's start. It's a great pleasure to have Huang from East China Normal University to give the quantum symmetry seminar today. She will talk about two-character theory of finite two groups. Please.
Okay, thank the organizer of this seminar and thank Professor Wang for his introduction. Today, I'm going to talk about the two-character theory of finite two groups. And this talk is mainly based on my recent work joined with Xu Hao and Zhang Zhihao. Today's talk is divided into four parts. The first is two representations of finite two groups. The second is what is the true character for a true representation and its intuition from TQFT. The third part is the orthogonality of two characters. Last, I will give an outlook of this two character theory. Okay, now let's go into the first part. What is a true group? A true group is a monoidal category G in which every morphism is an isomorphism and each object X is invertible. That is, there exists an object Y such that X tensor Y is isomorphic to the tensor unit, so is Y tensor X. We say a two group is finite if its homotopy groups are finite groups. Let G be a two group. Its first homotopy group, Pi1G, is defined to be the group of isomorphism classes of objects in G. And its second homotopy group, Pi2G, is defined to be the automorphism group of tensor unit of G. The two group structure of G is determined by its homotopy groups and the three cohomology class of, where the three cocycle of is the associator of G. And here, Pi1G acts on the abelian group Pi2G by conjugation. A finite semi-simple true representation of a true group G is a functor from BG to true vec. Here, BG is the true category with only one object star and the home category being this true group G. That is the one-point delooping of G. True vec is a true category of finite semi-simple categories, linear functors, and natural transformations. It is fully dualizable and categorifies the category vec of the finite dimensional vector spaces. In other words, a finite semi-simple true representation of two group G is a finite semi-simple category equipped with a G action. And this category consists of finite semi-simple true representations denoted by 2rep G. Recall that for one group G, the representation category rep G is equivalent to the category of modules over the group algebra KG. To study the true representation to category 2rep G, we want to find a true group algebra we denoted by vec G that had the same similar property. We construct the true group algebra vec G in two steps. The first step is to linearize the home space of G. Then we obtain a K-linear monoidal category denoted by K star G. And the endhome algebra of every object is isomorphic to the group algebra K pi 2G. And the second step is to take the Karoubi completion of it. By the universal property of Karoubi completion, finite semi-simple true representations of G are equivalent to the finite semi-simple modules of vec G. So vec G is our expected true group algebra. Besides, when G is finite, vec G is equivalent to the direct sum of Pi1G copies of rep Pi2G, and hence is finite semi-simple. Since Karoubi completion preserves rigidity and G is rigid, vec G is also rigid. Therefore, vec G is a multifusion category that is finite semi-simple rigid monoidal K-linear category, which is also a categorification of semi-simple algebra. Okay, now we want to consider the structure of this two-category Chirac-G. By a theorem of Douglas-Ruther, a linear two-category D is finite semi-simple if and only if there exists a multifusion category C, such that D is equivalent to the two-category of finite semi-simple left C modules. Therefore, Chirac-G, which is equivalent to this module category, is a finite semi-simple two category. This categorifies the classical mask theorem, which says that rep G is finite semi-simple for finite group G. Moreover, for two finite semi-simple two representations, the Ling tensor products admit a diagonal G action as follows. This defines a symmetric monoidal structure on two rep G. The rigidity of two rep G is due to that of two egg. More explicitly, both of the left and right dual of V is given by V op equipped with the G action as follows. And the inverse objects G inverse here is the dual of G. Thus, is unique up to an unique isomorphism, and the evaluation map one morphism is the home functor, and the co-evaluation one morphism is defined by sending K into this direct sum. Therefore, two rep G is a symmetric fusion two category, that is finite semi-simple rigid symmetric monoidal two category, and the tensor unit is simple in the sense of Douglas and Ruther. Okay, based on the definition of two representations, now we want to talk about two characters on it and the intuition from TQFT. Recall that for a group G, the character of a representation V rho in rep G is a function from G to K defined by taking the chase of rho G. Now we want to categorify this notion. First, we know that taking chases in VAC can be generalized in any rigid symmetric monoidal category, and we can see the following graph calculus. Then the rigidity of two VAC provides a categorified notion of this chase. For a finite two group G and a true representation V, we defined the true character chi V by taking its value on G to be the composition of these three functors that follows. And since the K linear functor category from VAC to itself is equivalent to VAC, we can identify chi V of G with a vector space. Therefore, chi V is a functor from G to VAC. And by a direct calculation, we have this equivalent definition of what is a true character for a true representation. And this coincides with the categorical chase defined by Gunter and Kompronoff. Okay, for a character chi V of one group G, it has a conjugation invariance. Similarly, the true character chi V we defined above has the following conjugation invariance. For any G and X in this true group, there is a canonical isomorphism of vector spaces. We denote it as psi GX from chi V of X to chi V of GX inverse by sending this natural transformation to this composition of three natural transformations. Moreover, this isomorphism renders the following diagrams commutes. And this isomorphism provides chi V a structure of the homotopy G fixed point, where the G action is induced by the conjugation. Thus, chi V is promoted to an object in the equivariantization of this functor category from G to VAC. Moreover, there is an equivalence phi from VAC G to the functor category from G to the VAC, where the first equivalence is induced by the functor from G to G up that send each morphism into its inverse, and the second is Yoneda embedding. The last one is the universal property of Kurobe convolution. Furthermore, phi is an equivalence of G modules, where the G action on the both are induced by conjugation. Thus, we obtain an equivalence between their equivariantization phi from the Drinfeld center of VAC G to the G equivariantization of this functor category. And under this equivalence to character chi-v can be also viewed as an object in this Drinfeld of VAC G. Here is a remark that the monoidal structure on the functor category from G to VAC transferred from VAC G is a day convolution as follows. Now we discuss a topological quantum field theory point of view on the two character. Let C be a symmetric monoidal two category. A truly fully extended frame TQFT, which is valued in C, is a symmetric monoidal two functor Z from the Cope 2 frame to C. And the cobordism hypothesis by Stolen and Lurie says that they send a single point to a fully dualizable object, and conversely, any fully dualizable object in C determines such a TQFT. And the key point is that the single point is fully dualizable in this cobordism 2 category, and the Cope 2 frame is freely generated by the single point. So we can decompose every manifold into small pieces and compute the value of TQFT on this manifold. Since the true representation V in 2-rep is fully dualizable, it determines such a truly fully extended TQFT. But here we consider the truly fully extended GTQFT valued in 2-vec, that is a symmetric monoidal two functor from Cope 2G to 2-vec, where this cobordism category is a category of 2D cobordisms equipped with G structures. And a G structure on the manifold M is a continuous map from M to the classified space of G. Here's a remark that the classified space of G is a CW complex. It has 0 cell star, and its one cell corresponds to the objects of G. Its two cell correspond to the morphism of G. And moreover, its first and second homotopy group is isomorphic to those of G, and the higher one is trivial. In this true cobordism category, a single point is not only fully dualizable, but also equipped with a G action. Then the cobordism hypothesis for G manifold says that a truly extended GTQFT is determined by its value on a single point, which is fully dualizable object equipped with a G action. So if we view this two representation V as a fully dualizable object in 2-vec equipped with a G action, it determines a truly extended GTQFT. In this true category, a circle S1 equipped with a G structure is a one morphism from the empty set to itself. So what does a G structure on S1 look like? First, we fix a point star in S1 and consider the pointed continuous map F from S1 to the classified space BG. Up to homotopy, F should map the complement one cell S1 without star to one cell in this BG, which corresponds to an object G in this true group. And this object G can be viewed as an holonomy around the circle, depending on the fixed reference point. So for every G in this true group, there is a circle in this coordinate category with a holonomy G. We denoted it by S1G and depict it in the following figure. Here, the holonomy is depicted by the defect labeled by G, which is the Poincare dual of the one cell S1 without star. And this is very similar to the figure appeared in the graph calculus of chi V of G. Since CV that TQFT sends the single point into V, we can decompose S1G into small pieces and compute that is the value of ZV on it is exactly chi VG. And the intuition from graph calculus agrees that from TQFT. So briefly speaking, the true character chi V is the value of TQFT ZV on the circle. The conjugation invariance of chi V can be also understood from this TQFT point of view. For every GX in this true group, the following figure depicts a two isomorphism from S1G to S1GX G inverse in this coordinate category. Here, the G structure on the cylinder is depicted by the defects labeled by G and X. Hence, a G structure on S1 is determined by the conjugacy class of the holonomy G. By decomposing the cylinder into small pieces, we can show that the image of this cylinder on the ZV is exactly the conjugation invariance mentioned above. Moreover, we could also see a pi1g action on the dimension of V from TQFT point of view. For a finite semi-simple category C, we define its dimension as the space of natural transformation from identity functor to itself. Then for the true representation V, we have the dimension of it is isomorphic to the chi V of E, and E is the tensor unit of G. The conjugation invariance provides a pi1g action on the dimension of V. For every G in this true group, there is an isomorphism induced by psi GE as follows. From the TQFT point of view, this isomorphism is an image of the following cylinder on the ZV. And it is well known that for a truly TQFT, its value on the circle S1 is a commutative Frobenius algebra. Here we expect that the true character chi V as a value of ZV on the circle should also have a commutative Frobenius algebra structure. For example, the value of ZV on the following pens should give the multiplication map. Indeed, these pens give a map from chi V of H tensor chi V of K to the chi V of H tensor K, and the obvious associativity implies that chi V is actually a Lax monoidal functor, and which is an algebra in this functor category from G to VAC, with the tensor product being the deconvolution. To understand the algebra structure on chi V, we need another point of view on TQFT ZV. It is a topological string theory with the target space BG, and it is also called the G-gauge theory. Here are some basic ideas and intuitions of this string theory. There are two types of strings, the closed string S1 and the open string interval. The strings can move on a target space X. And a string configuration is a map from S1 or I to X. Such a map is equivalent to a background gauge field on the string. And we are mainly interested in the space of string configurations, that is the space of mappings from S1 or I to X, or the functions on this space. Given a TQFT, or a topological string theory, it maps a string with a background gauge field to a vector space. So it gives a vec-valued function on the space of string configurations. The value of a TQFT on the open or closed strings is called the open or closed string algebra. Now we take the target space to be the classified space of G. Then the string configuration or background gauge field as a map to BG is the same as the G structure. The space of closed string configurations is a mapping space from S1 to BG. But we will not study this mapping space directly, but use a category to model it by the homotopy hypothesis. We have the fundamental group of S1 is isomorphic to Z, and higher is trivial. Thus, we use the groupoid BZ to model S1. Indeed, BZ is equivalent to the fundamental groupoid of S1. And it is natural to see the true groupoid BG to model the classified space of G. Then the mapping space can be modeled by the functor to category from BZ to BG. This is also called the loop to groupoid of G, denoted by LG. The functor to category from LG to VEC is a space of functions on the space of closed string configurations. And by the previous discussion, the true character KV as the closed string algebra should be an algebra in this functor category from LG to VEC. For one group G, it is well known that the loop groupoid LG is equivalent to the action groupoid, or we call it the homotopy quotient of G, well, G acts on itself by conjugation. Moreover, we have this functor category from the homotopy quotient of G to VEC is equivalent to the Drinfeld center of VEC G. And these notions and results can be easily generalized into two groups. Here we give the definition of homotopy quotient. Let G be a true group and X be a groupoid equipped with a G action. The action true groupoid or homotopy quotient is the true groupoid defined as follows. Its objects are objects of X, and the one morphism is a pair, and the first component is an object, G in this true group, and the second component is a morphism in X. And true morphism between these pairs is actually a morphism in two group G, such that the following diagrams commute. Okay, here comes our proposition. Let G be a finite two group when G acts on itself by conjugation. The action to group points is equivalent to the loop to group point LG. Moreover, the functor to category from LG to VEC is equivalent to the Drinfeld center of VEC G. Hence, it admits a braided monoidal structure. And we expected that the true character KV as the closed string algebra we mentioned before should be a commutative algebra, and this functor category from LG to VEC, which is isomorphic to the Drinfeld center of VEC G. Similarly, the space of VEC-valued functions on the space of open string configurations is the functor category from G to VEC, which is equivalent to VEC G. And the open string algebra should be an algebra in it. But in general, the open string algebra depends on the boundary conditions or debrains. That is what we assigned to the boundary points of the open string I. Given a closed string algebra, there are many compatible open string algebra depending on the boundary condition. The following path is a multiplication map of open strings with different boundary conditions, and they are labeled by different colors. There is a very important phenomenon in string theory called the open-closed duality, which suggests that the closed string algebra and open string algebra are related in a non-trivial way. And the open-closed duality has been extensively studied in 2D TQFT and 2D CFTs in these literatures. Here are some basic phenomena. The open string algebra is the internal home of the boundary conditions, and the closed string algebra is the full center of the open string algebra. The boundary block relation in topological orders can also be viewed as a variant of the open-closed duality. Now we come back to the G-gate theory. Recall that our input data is the finite two-group G and the true representation V. The category V is assigned to the point, so it plays a role of categories or boundary conditions. In other words, the boundary conditions are objects V in this true representation. Then the open-closed duality stresses that the open string algebra should be the internal home of V and V, living in the vec G, and the closed string algebra should be the full center of this internal home in the Drinfeld center of vec G. When the true representation V is reducible, the Morita class of this internal home is independent of the choice of non-zero V. Its full center is also the full center of the category V, which is a Lagrangian algebra. And here's a remark that in a non-degenerate braid fusion category V, a Lagrangian algebra A in B is a commutative connected separable algebra that is maximal, in the sense that the category of local A modules is equivalent to vec. Recall that we have an equivalence from the Drinfeld center to the G covariantization of this functor category, and then we obtain our main theorem by the direct calculus. Let G be a finite two group, and V is a true representation that is irreducible. There is a canonical isomorphism from phi ZV to chi V op in the G equivariantization of this functor category. Hence, irreducible to character chi V admits a structure of a Lagrangian algebra and this equivariantization inherited from the full center of V op. And here's a remark that in general, vec G is a multifusion category. Then the Drinfeld center of vec G is equivalent to this G covariantization is a braided multifusion category, which is the direct sum of non-degenerate braid fusion categories. By a Lagrangian algebra in the Drinfeld center of vec G, we mean a Lagrangian algebra in a direct summand. Moreover, the isomorphism classes of Lagrangian algebras in the Drinfeld center are one-to-one corresponding to the equivalence class of indecomposable vec G modules. That is a reducible true representation of this two group G. Thus, the true representation are completely determined by their two characters. Okay, now let's go into the third part, orthogonality of two characters. At first, we mentioned that chi V is a Lagrangian algebra in the Drinfeld center of vec G. Now we look at lemma on the Lagrangian algebra. Let B be a non-degenerate braid fusion category and AB be the Lagrangian algebras in B. Then these module categories are fusion categories whose Drinfeld center are equivalent to B as braid fusion categories. Physically, this non-degenerate fusion category B can be viewed as a truly topological order, and the Lagrangian algebra AB lead to anion condensations and produce two 1D boundary topological orders R mod A in B and R mod B in B. The 0D domain wall between these two boundaries also form a category denoted by M as follows. For fusion category C, the isomorphism class of Lagrangian algebras are one-to-one corresponding to the equivalence class of indecomposable C modules. The category M is the indecomposable R mod A in B modules corresponding to the Lagrangian algebra B. And this Lagrangian algebra is also the full center of M. Under the forgetful functor from the Drinfeld center of this module category to itself, the image of B is B tensor A. So we have an algebra isomorphism that B tensor A is isomorphic to the full center of M in this module category. On the other hand, the full center of M can also be written as this direct summand. It follows that the home space in B from the tensor unit to B tensor A is equivalent to the dimension of M. Now we take B to be the Drinfeld center of fusion category C and AB to be the full center of two indecomposable C modules. And the results gives that the dimension of this functor category is equivalent to the home space in the Drinfeld center of C. This result still holds when C is a multifusion category. So we take C equals to the vec G for a finite two-group G. In this case, we will get the following equivalence. And under the equivalence file we mentioned before, the right-hand side is home space of this G covariantization of this functor category. Home space from the tensor unit to the chi V tensor chi W, and the tensor here is the day convolution. And we define this home space as an inner product of chi V and chi W. And for F and G and the C covariantization, their inner product is defined to be the home space as follows. Moreover, the inner product is also isomorphic to the pi1G fixed point of the following space, where the pi1G action on the space is induced by the G equivariant structure on this F tensor G. Here comes the theorem of the orthogonality of two characters. Let G be a finite two-group and VW to be the true representation. There is a canonical isomorphism from the inner product to this to the dimensional of this functor category. And recall that for a finite group G and VW in rep G, we have the following orthogonality of characters as follows. So our result is a categorification of this classical result. There are some interesting observations and problems. We will discuss these topics in the second version of our work. The first question is about the maximality of the Lagrangian algebra chi V. Recall that the commutative algebra structure of two-character chi V can be obtained by taking its value on TQFT Z V on some cobordisms. Can we obtain the maximality of the algebra chi V from the cobordism point of view? We believe that this maximality is related to the modular invariance. For a rational TQFT, the equivalence between them is improved in Kongliang and Runkun's article. And the second observation is a numerical definition of true character for G and H in this true group. And the morphism A, we can define the joint true character as follows. From the TQFT point of view, this joint true character is a partition function of ZV on the following torus. As a partition function of a torus, the joint true character has an obvious modular invariance. Moreover, when G is an ordinary group, it recovers some classical notion of character and also gives a geometric understanding of the modular invariance of the character of Lagrangian algebra in the Drinfeld center of vec G. It is interesting to study the joint true character, and we believe that there are connections between joint true characters, Lagrangian algebras, or true characters, and the modular invariance. And that's all. Thank you for listening.
Interesting talk. Are there any questions? I think so.
Can you hear?
Yes.
I have a very, very basic question from the first slide about the definition of a two group. So is it true that every group has a two group structure? You can put a two group structure on every group.
Sorry, can you speak a little bit louder?
Maybe speak to that. Yeah.
So is it true that every group has a two group structure?
So if I give you any group, can you get a two group?
You mean from construct the finite group into two group?
Yeah.
Okay. You can take it because you could take all the elements of one group into the objects of two groups, and then the morphisms are identity morphisms.
The classification of all the possible two group structure for a given group. Is there some
Sorry, can you repeat that again? Because I can.
So how do you classify two groups? I think in your first few pages, you talk about the homology data. Can you show us again?
Okay. This one.
Yeah.
Yeah, we use the skeleton of this category to fix the structure of two group, and moreover equipped with associator.